the quiz will not directly cover any MATLAB coding kind of things, but it will indeed cover the concepts where for some small problem, I can ask you to actually construct element stiffness matrix, or the global element stiffness matrix in the global coordinates. How do you do transformation? Those kinds of things. Conceptually, you need to know how to do that. And for a small problem, I can ask you to do that. I won't ask you to write a MATLAB code for the quiz. But if you've done the homework problems, it would be very similar. Something that you did by hand, it would be very similar to that. Okay. Any other questions? Go ahead, Yiqing.
So for incline support, would you be able to use like 0 for the XY axis and then the angle for however you incline?
So in the MATLAB code, yes, for the inclined supports, wherever you have an inclined roller support, you would use the degree of freedom 0, as I called it in the code. But in the quiz, or in, for example, in the quiz, if I gave you an inclined support and asked you, and if I could, so here's a sample problem just off the top of my head. Yeah, I have a triangular truss and one of the supports is inclined. I could give you the global stiffness matrix for that truss, and I could ask you to tell me what the transformation matrix for that global truss would be to convert that global stiffness matrix to the rotated. So for example, maybe if I go back to this particular example, where I had this truss with an inclined support, I could tell you what the global stiffness matrix for this truss is, which would be on the next page of the handout. I could tell you what this stiffness matrix is. And then I could ask you, what is the global transformation matrix, right? I would not ask you to actually do the multiplication for this times that times that. Matrix multiplication, of course, is very cumbersome and takes a lot of time. So whatever you'll get a small problem that you can do by hand or using a small calculator. But it would use all the concepts that you should know if you've written, or if you understand the MATLAB code, what it is exactly doing, and if you understand the stiffness method. Make sense? Go ahead, Nikhil.
So both force method and stiffness method, the computer.
Yeah, so force method, the flexibility method is a little more complicated. And no, I don't expect you to, although the flexibility method we've already covered in the previous quiz, so it's not there. But I can ask you to systematically construct, for example, things like this. For given this truss, this is a determinate truss, construct the system of equations that governs equilibrium for this truss. I can ask you that. Okay. So yeah, take a look at the sample quiz once I get it posted up. And if you have more questions, I'll be happy to answer them again on the discussion forum. All right, any other questions? Okay, so let's start with this related but new topic, again for the stiffness method. The idea would be, as I told you, for the stiffness method is that we want to decompose a structure into its component parts. And then we find the relationship of force and displacement for each one of those components, rotate them into a common system, and then assemble them to enforce equilibrium, right? So this is sort of a general concept that is applicable to any structure, not just trusses, the way that we've looked at. So today we are going to look at what or how we can apply this same concept to beam type structures. So here's a simple beam type structure with simply supported beam with a overhang tip load applied here. And the question could be that you want to find the displacements and rotations at different places in the beam. You want to find the reactions and so on. And once again, even for beams, it does not matter whether the beam structure is determinate or indeterminate. Exactly the same stiffness method, if you remember from trusses, exactly the same stiffness method works for determinate or indeterminate trusses. So here as well, it doesn't matter. And the overall idea is also very similar. You kind of define the geometry of the problem, which for beam problems means, again, certain nodes. So I'm calling node 1 this point, node 2 this point, and node 3 at the tip. In addition, I'm saying that node 1 is connected to node 2, node 2 is connected to node 3. So very similar description as we had for the truss problems, except now that each member can not only have tension or compression, just like the truss members, they had tension or compression, but now the beam can actually bend. It can have rotation in addition to tension and compression. It can have bending, right? So we'll talk about how do we describe those degrees of freedom, and loading and boundary conditions, and although are generally specified. So this is all information that would go 1 to 3. This is all information that would go into an input file for such a beam structure, and I will show you an example of that too. And as I mentioned, the idea really is here that if I have a long beam made out of beam elements such as this, if this is one beam element, I want to be able to describe what would be the forces and moments needed to have a displacement of delta I. So if, for example, if this is node I, this is node J, so think back to your truss force displacement relationship. Node I, node J, element M. I want to be able to tell that if there is a displacement at I, what would be the forces and moments required at the two ends to do that? If there is a rotation at I, what would be the forces and moments needed to do that? Similarly, at J, displacement and rotation, what would be the forces and moments needed to get those displacements? That is exactly what we did for the truss problem also, if you remember, right? And once we can do that, we'll call that relationship in the same form, Qm is equal to Km times dm. This is force, Q is the force, d is the displacement, so that would be the element force displacement relationship that I'll tell you how to do that. And one good thing about beam problems is that we can easily orient our beam along the x-axis, no matter whether it's vertical, but we can orient our beam problems all along the x-axis. So the local coordinate system and the global coordinate system will always be horizontal, which helps us how? Miles? We don't have to do transformation from inclined coordinate systems to horizontal and vertical, right? The global and the local coordinate system are the same, so there is no need for transformation for beam problems. A little bit later, we'll look at frame problems. In frames, it is really a beam which is at an inclined angle. There, we would have to do transformation to bring it back to global coordinate system, okay? So, but for beam problems, we don't need any transformation. And at the end of the day, we'll assemble, just as usual with the trusses, we'll assemble a system of equations which would look exactly or very similar to the truss system, and we can solve that very easily for the free displacements and the specified reactions. Okay. So here's an example of how we would decompose a beam structure. If you look at any particular element in the beam, that element might be connected to nodes I and J, and I'm calling it element M. So there would be degrees of freedom associated with it. Normally, if you remember, for the truss problems, we said 2 degrees of freedom per node, right? But for beam problems, we will neglect axial deformations. Okay, so we are neglecting axial deformations, meaning that the displacement at both those ends would be exactly the same. So that is not really a true degree of freedom. But in addition to the horizontal and vertical degrees of freedom, a beam also has a degree of freedom of rotation. So these would be the degrees of freedom which we would call uh, by basically transverse displacement, transverse to the beam axis, it would be a transverse displacement and rotation at each of those nodes. So there are these 2 degrees of freedom at each node, okay? And since there are 2 degrees of freedom, for example here, 2 degrees of freedom per node, so let me cancel out the horizontal degrees of freedom in this beam structure as well. And if we number the degrees of freedom, so node 1 has degree of freedom 1 for the vertical displacement, degree of freedom 2 for the rotation. Similarly, node 2 has degree of freedom 3 for the vertical displacement and 4 for the rotation, 5 and 6 at node 3. So very similar to what we had in the truss case, just that the physical interpretation of the actual degree of freedom is different. It's not both displacements. One is a transverse displacement and the other is a rotation. What would be the degrees of freedom for node I? If I have a general node I, what? Say again? 1, 2 would be for node 1. So for node I in general, it would be 2i minus 1 and 2i, right? So transverse displacement we'll call 2i minus 1 and the rotation would be 2i. Similarly for j, 2j minus 1 and 2j. So if I have a beam structure with n total nodes, the total degrees of freedom would be 2n. Okay. Later on we'll see for frames it will actually be 3 degrees of freedom. So it does matter how many degrees of freedom per node you have. But for beams, the picture is much simpler. Now, as I mentioned, what we want to do is we want to take up a long a beam structure, divide it up into elements, and then we want to find the local force displacement relationship for each element. So this is the most critical part of stiffness method for beams. How do we find out that a beam element that was initially in this black configuration, and if for some reason, for applied loads for instance, or for whatever support settlement or something, if node I moves by an amount delta I, node J moves by an amount delta J, and in addition to that, there is some rotation at node I and node J, theta I and theta J, then can I figure out that in this new blue deformed configuration, what would be, excuse me, what would be the forces at nodes I and J? Those are what I'm calling Qi and Qj. And what would be the moments at the nodes at those nodes? So that's what we want to find. How do I relate these 4 degrees of freedom, displacements and rotations at the 2 ends, with the forces and the moments at these 2 ends? This is the relationship that we want to find. And one way to do that is to actually find out 4 simpler cases. 4 simpler cases of displacements. One is a displacement at node I. So again, looking at this beam element, if I have node 1 and if I give it a unit displacement, making sure that all the other degrees of freedom remain 0. Okay, so if you look at this shape is such that only displacement at node I is given delta I, and all the other degrees of freedom are 0. No rotation here, no rotation or displacement here. Okay, and if I can figure out what would be the forces and the moments needed to cause this type of a deformation, then I know that then I can use that information to construct this relationship. Okay, and the idea is that since I have only 4 degrees of freedom, I'll do this process 4 times, once for a displacement at I, rotation at I, displacement at J, rotation at J, and then no matter what configuration I have here, I can always express that configuration in terms of some combination of these 4, right? Do you agree that if I have a particular beam element and by using these 4 different configurations, if I add, if you give me any configuration of a beam element, I can always generate that particular configuration with some combination of these four, right? And if I can generate that configuration, then I can use this information to calculate the relationship between these forces and moments and the displacements and rotations also. So ultimately what we are looking for is these set of forces which I've labeled here, and a quick word about this also. Note first of all that the positive sense of the degree of freedom, for displacement I and displacement J is pointing upwards. Okay, so if you look at the previous example, we drew at every node, we said horizontal displacement, vertical displacement, and rotation. That is showing the positive sense of that degree of freedom. Okay, now in contrast to the positive sense of degree of freedom, let me ask you this. This Mi is something that I would call a positive moment, right? This moment is pointing in the same direction as this rotation, which is the positive sense for the degree of freedom. This is a positive moment for the force element, force displacement relationship. But would you call that a negative bending moment or a positive bending moment? It would be a negative bending moment, right? If I apply a moment to a beam at the end, which looks like this, is going to cause a frowny face. Of course, that's a negative bending moment. So, but that is not a problem because the stiffness method does not rely upon bending moment or moment area method or anything like that. It relies upon the force displacement relationship using the degrees of freedom. And as long as the rotation degree of freedom and the force or moment degree of freedom are aligned in the same direction, things will work. And I'll come back to this point a little bit later as well. Can somebody think of another one of these forces and moments where the convention that we use for bending moment and shear force diagrams is opposite? What would be? So I just told you that moment here looks like a negative bending moment, but for the stiffness method, it is a positive nodal moment. How about this force? A shear force on the left end of a beam should be pointing up. That's what we treat positive, correct? How about shear force at the right end of a beam? Pointing down is what we call positive. So this Qj is also opposite to our regular beam shear force diagram and bending moment diagram convention. But again, that's not a problem because this Qi is pointing in the positive direction for the degree of freedom. So as long as we are calculating these relationships consistently, it will not affect our results with the stiffness method. So let me write out these forces and moments. For we have Qi, Mi, those are the force and moment at node I, and similarly Qj and Mj, those are the force, transverse force, and the bending, not bending moment, but node moment at node J. And what we want is to relate it with delta I, theta I. Those are the displacement degrees of freedom at node I, displacement and rotation, and similarly displacement and rotation at node J. So the relationship that we are looking for, is this relationship. How do I relate each one of these forces to each one of these displacements? And we'll do that by doing these four cases. Let me ask you this. What would be the size of this matrix? What would be the size of this matrix? 4 cross 4. Yeah, so we have four displacement and rotation degrees of freedom, 4 forces and moments, which was actually exactly the same size for a truss element as well, right? There were 2 degrees of freedom per node for a truss element. There are 2 degrees of freedom per node for the beam element. So no wonder the size also is exactly the same. We have 4 cross 4, sorry, 4 cross 1. 4 cross 1, forces and moments, stiffness, element stiffness matrix, and displacement vector. So let's see how we can come up with this 4 cross 4 matrix. Once we've come up with this 4 cross 4 matrix, we can use it for any beam element. We can use it to solve all types of beam problems. So I'll give you an example of how you would come up with say the force displacement relationship for element case 1, and I will ask you to do case 2 as an in-class exercise in a little bit. So let's make sure we understand what's going on here. And I've already actually computed that, and I'm just summarizing it here. This is what the element force displacement relationship should look like. This is the 4 cross 4 matrix that we are going to try to derive now using 4 cases at a time. So let's see, case 1. Case 1 is this case where we have a displacement at node I, no rotation at node I, no displacement or rotation at node J. And what we want to do is to find out that if I apply a force Qi here, what would be the displacement delta I? Okay. I want to find out Qi, Mi, Mj, Qj, all of those 4 things in terms of the value of delta I. So any ideas how we can do this? How can I relate this load Qi or force Qi to this displacement delta I? How could we do that? Maybe let me pose the problem in a different way. Let's say there's no Qj, Mj, Mi, and all that. There's no there's these. You can think of those as reactions. So maybe I'll draw that. So this is not there. This is not there. This is not there. And this is not there. And let's say I'm just applying some load P. So can you tell me, if I tell you what is this load P, can you tell me what the displacement would be in terms of P? Right? And how would you do that? Anyone? Go ahead, Miles. You could use virtual work method. But before we do that, is this structure determinate or indeterminate? Frederick? Determinate? Is it determinate or indeterminate? Indeterminate. Why? Because one end is fixed. Immediately, the simplest determinate structure would be a cantilever beam with one end fixed. In addition to that cantilever beam, we have a vertical roller here, right? So the degree of indeterminacy is 1, right? I don't have any. Actually, technically, it's 2 because the horizontal reaction is also unknown. But since we are accounting only for vertical directions, we can treat it essentially as a degree of indeterminacy 1. Okay. Now back to that question: how do I relate P to delta I? If it's indeterminate, what do I need to do to find that relationship? Yep, force method, right? Force method, where I would use this as I would draw this as a system of two a structure with two subparts. So plus the same structure. So this is the underlying determinate structure, cantilever beam really. And I will change back the force to call it Qi. Essentially, I'm trying to relate Qi to delta. So I have this applied force Qi, and in addition, I want to have zero rotation here. So this is some moment Mi. So if I apply the right amount of moment, I will get zero rotation here. Does that make sense? Both of these are determinate problems. So for this particular problem, the bending moment diagram would look like this. The value here would be positive Qi times L, L being the length of the element. For this other case, I have bending moment like this, which is nope, not positive, negative. So the bending moment diagram for this guy would be negative Mi throughout. And the compatibility equation would be compatibility says that I want to find theta I prime plus actually maybe I should not call it theta I prime, but let's see, plus Mi times F, and actually since this is a rotation, let me call it alpha I equal to 0. Does that equation make sense? What I'm saying is that under this load Qi, I will get some displaced shape that might look like this, in which case I will have some theta I prime. And under this moment, I might get some displaced shape that looks like this. So if I add these two together in the right magnitude Mi, then I would get a zero rotation at this end. That's what this compatibility equation says. Make sense? Okay. So what would this theta I be? What would be the rotation at the end of a cantilever beam? Say again. Okay, yeah, moment area method. First theorem says theta at theta prime I minus excuse me, theta prime at L, which happens to be 0, should be equal to the area under the curve of the curvature diagram, which is nothing but Qi times L and half times another L. So Qi and divided by EI. So Qi L square divided by 2EI. That's the rotation. That's the rotation at this end, and I think I'm missing a minus sign. Right, because it should be theta L minus I, not theta I minus theta L. So theta I prime is equal to minus Qi L square over 2EI. And what is alpha II, which is the flexibility? How can I calculate that? Alpha II is the flexibility of this end I when I apply a unit moment here, right? So we could use maybe the virtual work method to do that. We could write it as integral from 0 to L of the virtual bending moment, which would be -1, right? So, and I'll write the virtual bending moment in red. Real curvature, which would be that -1 again, 1 over EI, and times dx. Does that make sense? I'm trying to find the rotation at this end now using the virtual work method. So what we get is L over EI, right? So what this allows me to calculate is using the compatibility equation. Using this compatibility equation, it tells me that MI would be equal to minus theta I prime divided by alpha I, which would be QI L squared over 2 EI, and L over EI. EI cancels off, one of the L cancel off. So that gives me a relationship between MI and QI. So MI turns out to be equal to QI L over 2. Sorry, go ahead, April. Say that again. Alpha II. MI. Yeah, so this is the is are you talking about this integral or the compatibility equation? The integral is basically, instead of MI, if I were to apply a unit moment, right? So yes, you're right. It would be MI prime in the numerator on both sides, which would get cancelled off, right? So MI turns out to be equal to QIL over 2, I believe. So that's one part of the problem. We still haven't related the displacement with QI. All that we did was to solve the indeterminate problem of what would be the reactions. So the reactions really are that there is a reaction of MI here, which we have just found is QL L over 2. We know that QJ would be simply equal to minus QI, right? Vertical force equilibrium. And what would be MJ? What would be MJ? So MJ plus MI plus QJ, QI times L should be 0, moment equilibrium, right? So using that, we can find this MJ, which would be equal to QI times L minus MI. Does that make sense? So all that we have done till now is to solve the indeterminate problem of all the reactions. We still haven't related the displacements. So let's do that now. Let me draw a line here to separate this. Okay. So now that I know that this MI is QL over 2, I can draw the bending moment diagram of the original problem that we were trying to solve. So for this problem, the bending moment diagram should look like starting with negative QIL over 2 and going to this guy, which would be actually equal to positive QI L over 2. Okay, so that would go up to this point, and the bending moment diagram for this problem would look like this. Note that this is the bending moment diagram of the indeterminate, the original indeterminate problem. Okay, so given that this is the bending moment diagram for this problem, what can I do to find delta in terms of this QI or QJ? Right, Nikhil? We can use virtual work. Let's do that. I can choose, and here's again, so most of you would, I would think, would choose either this as the origin or this as the origin. Is there a better choice? Right here. Let's choose this as the origin, which makes my equation very simple. The equation becomes QIX, right? And the limits are minus L over 2 to plus L over 2. So that would make finding out the displacement simpler. So we are using the virtual work method where we are applying a unit load at this end, and the bending moment diagram for that unit load would be simply L over 2 to minus L over 2 to plus L over 2. That would be the virtual bending moment diagram. The real bending moment diagram is exactly the same thing, but with QI. So delta I would be equal to integral from minus L over 2 to plus L over 2 of the virtual bending moment, which is the virtual bending moment is simply X. Do you agree? The virtual bending moment is simply X because if I apply a unit load, instead of QI, if I apply a unit load, that would be minus L over 2 to plus L over 2. So the virtual bending moment is positive X, and the real curvature is QI times X divided by EI, and we need to integrate that dx. So what we get is QI over EI times x cube over 3 between the limits minus L over 2 to plus L over 2, which can be simplified to QI over EI, 3EI, let's say, and L cube over 8 minus of minus L cube over 8, which equals QI L cube 2 over 3 EI divided by 24. That becomes 12. Sorry, not 24, but 8. That becomes 4. So it becomes QI L cube over 12 EI, which means we have the first relationship that we wanted. We have QI, and we have related QI to delta I. So I'll write that relationship right here. QI is equal to 12 EI over L cube times delta I. Okay. We've already found out that MI is equal to QL over 2. So we can write that here. QI times L over 2 would be 6 EI over L square. So 6 EI over L square times delta I. That making sense? And finally, QJ is nothing but negative QI, so that would just be minus 12 EI over L cube times, times delta I. And finally, MJ is mj is equal to also qil over 2. So that is also equal to 6ei L square times delta I. So let me finish this out and then I'll try to explain how this fits into that global picture. This is the relationship that we were looking for. Okay, how did we come up with this? We said that ultimately, actually, we are looking at this relationship. We want to find out the relationship between these four forces and moments and these four displacement and rotations. We said we will express this configuration as a linear combination of these four configurations. We picked the first one, we tried to solve it, and the way we did that was to actually break it up into two parts, and that allowed us to relate qi, qj, mi, mj amongst themselves using the force method. Once we have that, we find the displacement here that relates qi to delta I. Okay, so that's what we did here. We found that qi in terms of delta I gives me these values, and using that we related all the other things. Knowing these four relationships, can you tell me how I can express them in a matrix format? What we did here was really that there is only one delta I. The only degree of freedom that was non-zero was delta I, right? Delta I was non-zero. All the other 3 degrees of freedom were 0. So that's why I'm writing it as 0, 0, 0. These were the displacement degrees of freedom. And how can I express this relationship in this form? Any thoughts? If I take out delta I common, what I'm left with is this coefficient. So I can take actually all of these four values and I can put them in this matrix in the first column. Okay, and since all the other three values are 0 here, this first row, when multiplied with this column, it does not matter what the rest of the three values are right now, at least. The rest of the three values in all of the rows do not matter. So what we have just done is we have derived one of the columns of that matrix. Does that make sense, Frederick?
What do you mean by it doesn't matter?
It doesn't matter for this particular case. When we go to case 2, case 3, case 4, then one of these guys will be non-zero and this actually would be 0. So we'll derive the other columns in the exact same way using the other cases that I've told you about. Right now, all we did was derive the first column of this matrix, and hopefully you see that because it is the first number in each of those rows that will multiply this delta I. Okay. I don't think I have enough time to go through the case 2 and certainly not for the in-class assignment. But maybe after the quiz, when I return back on Monday next week, we can do this as an in-class assignment. And next lecture on Wednesday, this coming lecture on Wednesday, Dr. Liu will do a review session for the quiz. So let's stop here, and then I'll see you back next week. Dr. Liu will see you on Wednesday. All right.